Okay, I've handed back everyone's tests that are here. At least I believe I have. If you don't have your test, anyone here not have your test? No. Okay, so Tuesday I told you I won't be here next week. Keith Reese will be teaching class your call for test. Keith Reese will be teaching classes Monday, Tuesday, Wednesday, and Friday. For lab, the lab activity that I had planned is a little involved, and without a TA, I just can't do it. So I'm going to have Jordan, who is the tutor for the class, come and hear James and come, and he will help you work through some problems. You do need to come. You will need to turn in your work. So that's what we'll have for lab. So you don't need to do a pre-lab quiz either, since you won't be doing the lab. And the purpose of the pre-lab quiz is to make sure you know what you're doing when you come to lab. Okay, next, the exams that I've given out. The average score was 75%, and I broke it down by sections. The knowledge, 86%, application, 76%, and synthesis, 69%. Here's a breakdown of how many people got what letter grade on the exam. And you notice I said the people who got A's and B's, which is a total of 13 people, they're on course to get an A, because of course your exam grade is going to be lower than your final grade unless you are a very unusual student. Leslie, here's your test. So your things like your lab grade should raise your grade. Your homework grade should be raising your grade. Your reading quiz grade should be raising your grade. Your clicker grade should be raising your grade. So that's why I have those people are in good shape. If you got something that's in the C range, you're okay. You're probably headed for a B or C on the current course you're on. Of course, you could always improve. There's also the other way, but we try not to countenance that option. If you were one of the people here, and notice that's 11 people that got lower than the C range, make sure you do try to come to talk to me so we can find ways to reach success, right? Sometimes it's just strategy. Like one person I talked to on the middle section here, the application section, didn't answer those and just had to go guess and only guessed one of them right because time was spent on other things, to a very significant detriment to the grade. In fact, yeah. Sometimes it's just strategy. Sometimes it'll be studying strategies. There were a few people who, despite, the instructions to put your explanations, put no explanations for the synthesis, and so they lost needless points there. So, make sure you come talk to me if you didn't do well on the test, because I want everyone to have success. It's kind of important to me. And with that in mind, let's look at the test kind of in its entirety. So here is the test, equation sheet and cartoon. The first one there, 94% got that one. Yay, it was the second easiest one. The next one, though, how many significant figures? Only 78% got that. So it's kind of important to remember. Oddly enough, I was looking at my son's physics test, and this was essentially one of his questions as well. And you have any digit that's not a zero is always significant. And if you have a decimal, a trailing zero is always significant. I was looking at somebody's lab report yesterday, and the person had mass that's equal to 38.5 grams. I said, but with the balance, I told you have to measure to hundredths. And the student said, well, the last digit was a zero. That means something. Zeros are significant at the end of a number. And so the zero there was significant. The leading zeros in the decimal were insignificant. All those do is set the size of the number. So that only had 3 significant digits. The next one also, I was surprised because, of course, this was exactly a clicker question we had in class. How many confirmed spatial dimensions are there in our universe? And the answer is 3. up, down, north, south, east, west, or up, down, forward, backward, left, right. What makes them independent spatial directions? They're mutually perpendicular to each other. Or the word we use in math and physics circles is mutually orthogonal, in case you want to know. 93% got the next one, magnitude of G. 81%, which of the following will cause a car to accelerate? Once again, this is something that I believe, had as a clicker question in class. Acceleration is change in velocity, which means change in speed or change in direction. So the accelerator, the gas pedal and the brake will both change the speed, so those are accelerations. The steering wheel will change the direction, so that's also an acceleration. The turn signal, it just makes a light flash. Pressing the horn just makes a sound wave. Those aren't going to speed it up, slow it down, or change its direction. I was pleased that with the addition here, most people got the correct answer. That is, you have one number with 2 significant digits, one with 4 significant digits. You add them up, and it's not the number of significant digits that you have that gives you the answer. It is the greatest of the least significant digits. So the least significant digits were the 5 and the 1 that I indicated. The 5 is in the units position, so that's where your least significant digit is going to be in the answer, 3. Scientific method, most people got this right. I put that it must be correct on there just to emphasize that a hypothesis is an educated guess. It's a guess. If I guess your age, I might be correct, but I also might be wrong. And it's the same thing with a hypothesis. It's a goal to be correct, but it's not a requirement. If you disprove it, you've shown that it's not correct. And then you go back and modify it. Projectile problem, you can see this one here is the 5th hardest. It's fired vertically up with a speed of 5 meters per second. What will its vertical speed be when it returns to the same elevation? One could have answered this basically saying it's symmetric with height. I did it with equation here in my solution. I used an equation there. I put the symmetrical first. I put my equation, since the y final minus y initial is 0, that means vy final squared minus vy initial squared is 0. Hence, the squared speeds have to be the same, and since I'm just talking about the magnitude, so is the speed. The base units, most people got that. That was one of the easy ones. What quantity corresponds to the slope of the velocity versus time graph? Well, that's something we did in lab. We spent a couple lab periods focusing on that. So that one should have been easy, and most people got it. The easiest one here is the bicyclist. This one here, I think, was taken straight from the supplemental homework assignments. Cyclist traveling at this speed, brakes to stop at a traffic light with this acceleration. How long does it take? Well, you just use speed is equal to initial speed plus acceleration times time and calculate the time. Person standing at the edge of a cliff throws a rock straight up. And what's its position 5 seconds later? Once again, choose the right kinematic equation, put your numbers in. This one's surprisingly not easy. A student leaves the dormitory exactly 5 minutes before the start of class. If the classroom is 350 meters from the dormitory, with what average speed must the student walk? Well, the average speed is just the distance divided by the time. Now, you did have to remember that the time was in seconds, or I gave you minutes, but you need to use seconds here for your answer. But I did not put an answer there that would have given you one of these numbers if you put in, 350 meters divided by 5. So I wanted to make sure people know you have to change it. But that's all it was. The distance divided by the time. Okay, then the 2 car problems here. The first one, relatively easy. I don't know what in the world's going on there. With the Porsche Spyder, this is true numbers. They're all supposed to be true numbers, but in the one with the McLaren, I was off by a factor of 10. So it goes from 0 to 60 miles per hour in 2.2 seconds. And so to calculate acceleration, the acceleration is just the change in speed divided by the change in time. Well, we got the change in speed, we got the change in time, boom. Acceleration. You did have to make sure that even though I gave it in kilometers per hour, you need to shift that from kilometers per hour to meters per second to match the units for the answer. The Bugatti Veyron Supersport holds the record for the quarter mile. It took 9.7 seconds to do that, assuming constant acceleration, which is a clearly false assumption. Then what's the final speed of the car? Well, you go through and you say the average speed is change in position over change in time. And if the acceleration is constant, then the initial speed plus the final speed divided by 2 is the average speed. Initial speed was 0, so it just turns out that the final speed is 2 times the average speed. So you just calculate the average speed and double it. Then we get to the synthesis ones. And once again, notice the explanation was 3 points, the figure was 2 points. I was grading one yesterday where it looked like the person wrote the right stuff on the figure and then erased it all. That's the goal, is to have it there. So the key on this one is, notice this one here was getting into the harders, 13th easiest, which makes it what, 7th or 8th hardest, I forget. There's a total of 21, so you can do the math. So the slope is the speed. So I just need to find the slope at 8 seconds. Now, common mistakes people made, most people forgot to draw a line and find the slope of that line. That was the biggest mistake people made. A second mistake was there were quite a few people who tried to do this and find the slope of that line. Problem is, that is not going to be the slope at 8 seconds. That would tell them the average speed from 0 to 8 seconds, but not the speed after it's gone 8 seconds. So that was the second biggest problem that people made. So you draw the line, you find the slope of the line, and so you notice that I used 2 points, this one up here and this one down here, that were on the line I drew. Then we had graphical addition. Graphical addition, you have to add them tip to tail, and the resultant goes from the tail of the first to the tip of the last. This one was, I'm sorry, Corso, but it was taken exactly from the supplemental homework, and so I used the figure from the supplemental homework problem that shows the addition of the 2 vectors. So you have the one at the tip of the first, you put the tail of the second, the resultant there, and of course then you had to use your protractor, measure the angle, and measure the distance. So that was doing it graphically. Then you had to do it analytically. So analytically, you break them into components and add the like components. Then you use the Pythagorean theorem to find the magnitude and tangent to find the direction. So I drew each vector alone, broke them into components, added the components up. Here's my final resultant with the components. And then I use Pythagorean theorem to find the magnitude and tangent to find the angle. Now the one that was easily the hardest. Notice that the graphical addition was 12th easiest. It was right in the middle of difficulty. The second hardest one for everyone was the baseball player hitting the ball that is initially 0.84 meters off the ground. There were a lot of problems even drawing the picture. Some people had the ball traveling in a straight path from the starting point to the ending point. The ball has acceleration, gravity in the vertical direction, so it's going to change speed. It's not going to do a straight path. You have to resolve the initial velocity into components. You don't know what the velocity is. So that's an unknown. So for your components, you have the initial velocity in the x direction is v cosine theta, and the y direction v sine theta. And then you solve one direction. I chose to solve the x direction for time. So I used a kinematic equation and solved it for time from the x direction. And then I put that into the y direction, the vertical problem. And I'm left with an equation that has as the only unknown the speed squared. And so I just solved that for this, well, just obviously. I solved that for the speed. And of course, you have 2 answers, plus or minus 56.0 meters per second. We just wanted the magnitude. We already know its direction. It started going up. And then the final problem, this one here had a mistake. Should have been 6.6. And if you put 6.6 in there, it changes the answer to 200 meters instead of 20 meters. But I solved it with that number. I realized after handing out the test, the average acceleration for that Porsche being 12 meters per second squared, 66 meters per second squared, it should have dusted the Porsche in the 0 to 60. 6.6, yeah, that makes more sense. So the obvious figure for this, and I say obvious figure for this, the one that's going to be obviously helpful if you think about it, if you get to it, is making a graph of the position versus time for each of the two cars. The Reliant Robin, is traveling at constant speed, so its velocity as a function of time is just a straight line. Whereas the McLaren P1 is accelerating and starting from rest, so it's doing a parabola. And where the two cross, that's going to be where my answer is. And so you make an equation for the distance as a function of time for each car, equation for the distance as a function of time for each car, and then you set the distances equal, and you solve for, or you set the times equal, and then you solve for the distance because they also have to have the same distance. Then we have the calculus problem, which I won't go over right here. It is what we did in class. You have to use A equals dv dt, separate variables, and integrate is your concept. And so then the rest is just calculus. So that's a review of all of the test questions. Any questions about the test? Must have been thorough. Remember, if you didn't score well, come talk to me and we'll try to figure out how you can be more successful. Because you have a drop test, and if you scored like below 70 on the test, we'd really like that to be your drop test, right? And to score 90s the rest of the way and just say that test was an aberration. If you scored in the 90s, the top score was a perfect paper, well then, congratulations. I wanted to do one more problem before I start in with new material. This problem, I talked about Newton's universal law of gravitation in class, but I didn't actually talk about orbital motion and that kind of things. Just a really brief history. Tycho Brahe was a Danish astronomer who was famous for things like when he was in college, he and a classmate got in a little tiff. And so they did what any good nobleman would do. They decided to have a duel. They got out there and they had a duel. They paced off. They turned and fired. And Tycho clearly lost because he got hit in the nose and lost part of his nose in this duel. But he was a vain man. So unlike me, who would have been, let's try to make it so people can't tell that my nose is missing a chunk, he had gold or silver prosthetics made. So he, accessorized the new jewelry. What do you suppose that their little tip was about? That made him get shot in the face. I told you he was vain, right? You tend to think it's going to be something like that. Or maybe a girl. Or, it was over who was the better mathematician, who solved the problem right. That's pretty lame, I think. Okay, so Tycho was famous because he saw a new star in the sky. Now, you have to remember, back then, we had Aristotle come up with a theory that said that everything is going around the Earth in perfect circles. In fact, they're all on perfect spheres made out of the perfect material that is crystal. Aristotle believed if it's a beautiful theory, it has to be correct. He thought that was beautiful. He thought crystal was perfect, thought spheres were the perfect shape, so that's what it had to be. And in fact, the Catholic Church latched onto this and said, yeah, that's right. The Earth, because of sin, is imperfect. But out there, the rest of the world is perfect. And so that's why we have this. And so if everything out there is perfect, by definition, you can't improve on perfection. And so if you have a new star, that's a change that should not occur. And so he gained fame. Now, this was Tycho's nova. Nova just means new. Other cultures had observed lots of new stars. But the Europeans were, I guess, behind the times. So he became famous. The King of Denmark set him up with the world's greatest observatory, which was basically a building with a hole in the wall and angles measured on the wall, and he could stand and sight through the hole and see when stars passed the hole. He took very careful observations, and then he died. But before he died, he hired Johannes Kepler, and he said, I want Johannes to take over my work. So Kepler did take over his work. And although there was a legal battle, Tycho Brahe's family wanted everything, and Kepler would have nothing. They had a court battle, and in the end, Kepler lost, but he still didn't give the data to the family. And so he used that data, and he saw three things that changed our understanding of astronomy completely. One of them was he said that I can accurately predict the locations of the planets at any time if, instead of making them do circular orbits around the Earth, they do elliptical orbits around the sun. And then he said the period of the orbit is related to the average radius, what we call the semi-major axis. Well, the period squared is proportional to the radius cubed. And that the speed is faster when they're in the orbit, the speed changes, that we don't have a constant speed as we go around the sun. We're fastest when we're closest, slowest when we're farthest away. Those were observations that Tycho Brahe came up with by looking at the data. He didn't have any physics reasons for them. It was just the data matches this. So that would kind of be a model, right? It's a model. It's something that says, okay, it explains it, not necessarily true. Well, about 100 years later, we had Isaac Newton, and Isaac Newton came up with physics that explained Tycho Brahe's laws, or Tycho Brahe's, Johannes Kepler's laws. They are Kepler's three laws, after all. And so this is looking specifically at one of them. So I'm going to go through the work here for that law. I know probably a lot of people just solve this by looking in the book and saying, hey, here's an equation for it. But we're in physics class. It's the understanding why that's our goal. So here we have a problem. It says we have a planet that enters geosynchronous orbit. Geosynchronous orbit means that it's staying the same place with respect to the planet. Now, if you think about that very long at all, you realize it has to be over the equator if it's going to be geosynchronous. If it's not going over the equator, it's going to be moving north and south and over different parts of the planet. So it has to be over the equator and has the same period, the same time for an orbit as the planet has for rotation. These are really important on Earth. How many people have, at least at some point, had a satellite dish to pick up TV signals? A lot of us have. Well, you don't have a dish in your backyard that's constantly moving to aim at the satellite. Instead, that satellite is placed in a geosynchronous orbit, so you can just have the satellite pointing one place, and it's always pointing at the satellite dish pointing at the satellite. So those are very carefully regulated, and people have to pay high prices to get a spot on the band that's going to give you geosynchronous orbits. Surprisingly, things like satellite radio, if you have Sirius radio, the Sirius radio system uses what they call a constellation of satellites that are using what we call eccentric orbits, orbits that are very far away from circular. And with those eccentric orbits, they end up with their satellites, at least two satellites over North America at all times, but not in geosynchronous orbit, and it has to switch from satellite to satellite over time. So they found a way to get coverage that is not a geosynchronous orbit. But there is something about your Sirius receiver. It's not aimed at the satellite. If it was aimed, you would have to constantly be changing the aiming. Okay, so let's get to this problem. We have the spacecraft orbiting the planet. What forces are acting on the spacecraft? Gravity. And that's it, the end. Now, why did I start by asking you what forces are acting on the satellite? Or on the, well, it is satellite, on the spacecraft. Why did I start there?
Because you're in space.
Because I'm in space?
Yeah.
But like if this came up on a test, right, your physics is really on how you analyze the situation. At this point, it's kind of easy. For the first test, we had just one thing, kinematic equations for physics, right? So you can take every problem and say, oh, kinematic equations, let's apply it. Well, now we've learned about forces. So we have two things we can consider. Is this just a kinematic equation problem, or is this going to involve forces? And so I look at this and I say, well, it's going around a circle. To go in a circle, it has to have a net force. That triggers me. I need to look at the forces. It triggers me in a good way. Not like somebody says, you Scandinavian people are all, I don't know, whatever you'd say. So that's why I said, let's look at the forces. So if I have this object, what direction is the force? Okay, when you're doing forces, you have to determine what object do I want to look at the forces on. There's two objects, you make a choice. You got a 50-50 if you just blindly do it. Which one would you choose, Chumapa? Which one? The spacecraft or the planet? Okay, she said the spacecraft. That's the one I would choose as well. If you are a very anal physicist, you might say, but they both move. Both the planet and the spacecraft move. They're orbiting what we call the barycenter, the center of mass. But if you take the mass of the spacecraft compared to the mass of the satellite, which one's more massive? Obvious answer, the planet, by a lot. And so the barycenter, the average position for the mass, is very close to the center of the planet. So we, as a general physics class, treat the planet as if it doesn't move. The fact is the Earth orbits about the sun? Not exactly. It orbits at a point that's within the sun, but not the center of the sun, and that moves. The sun is also orbiting about that point, but it's within the sun, so it's just doing little wiggles. That's one of the ways that astronomers look for exoplanets, planets orbiting other stars. They look for the wiggles in the star that tells them that something is orbiting them. Okay, so back to this. We have that force of gravity. That's the only force. I said it's going in a circle. If it's going in a circle, what can you tell me about the net force? The sum of the forces toward the center has to equal, Newton's second law says, sum of the forces is mass times the acceleration toward the center. But if it's going in a circle, we have learned that centripetal acceleration is v squared over r. I better use a capital R to be consistent with my picture. The sum of the forces toward the center is the force of gravity. Okay. So I have force of gravity is equal to mv squared over r. Which m is that? Mass of the planet or mass of the spacecraft? Spacecraft, because my object was a spacecraft. In Newton's second law, that mass is the mass of the object I'm looking at. So I'll put S for spacecraft or spaceship. Well, what is the equation for force of gravity? You may not have it memorized. It's capital G, mass of the first object, mass of the second object, over the separation squared. Well, if you look at this, something really cool turns out. I have the mass of the spacecraft in both of those equations. So it's going to turn out for my answer, the mass of the spacecraft isn't even part of my relationship because it cancels out. I don't need to know the mass of the spacecraft. You might have said, they didn't tell me the mass of the spacecraft. There's no way I could calculate this because I have two unknowns, mass of the spacecraft and mass of the planet. But it's going to cancel. So I'm looking for the mass of the planet, so I just solved that for the mass of the planet. Multiply both sides. Well, first I'll write this. Multiply both sides by r squared over g mass of the spacecraft. And you see mass of spacecraft canceled. One of the r's cancels. I'm left with v squared r over g. Of course, did they give me v? No, they didn't give me v. But they gave me the time for one circular orbit so I can find it. It's doing a circular orbit, so v is equal to change in position over change in time. The period is the time for one orbit. Capital T is the symbol we use for period. So that's period. So in one circle, it has time period. What's the distance for one circle? We call it the circumference, and it's 2 pi r. So that's the speed. And so there we have an equation for the mass as a function of the radius, and I forgot where'd the period go? And the period. I forgot the over t when I put the speed. I just put the circumference. And so that's the end of the physics. Part B is just put your numbers into the equation. And your answer should be somewhere about 10 to the 26 kilograms, which is a reasonable mass for a planet. For a planet like ours. So the physics here, I wanted to make sure we go through that and not have people just say, oh, there's an equation. Let's just use that equation. I want you to know where it comes from because that's where the physics is. So Newton came up with a physics explanation for Kepler's laws, which made Newton's laws very quickly accepted because suddenly you have explanation for something that was well accepted already. Kepler's laws were well accepted at that point. One more thing that's just of interest before we get to work and energy. Wow, I've got 18 minutes. I probably won't get my demonstration. Dr. or Keith Reese will be able to do that. The Coriolis effect. How many people have even heard of the Coriolis effect? So I can guarantee you when I was in this class, I had not. So we got about 4 people who raised their hand. The Coriolis effect leads to what we call the Coriolis Force, which, like centrifugal force, is fictitious. It doesn't exist. And you might wonder, why do we talk about these things that don't exist in physics class? It's because the word force is not correct, but the effect is very real. So let's just talk about that effect in very simple fashion. Here we have pictures of a merry-go-round, or something like that, a carousel. So in the carousel, if you are on the carousel and you are near the middle, and you throw something. Now, if you're going around a circle, and you're not at the center, then you have a velocity. So in this case, position A has a velocity like that, right? At this moment, it has a velocity like that. If you throw it straight outward, so if you throw it from position A toward position B, you have a sideways velocity plus the velocity that you put toward B. So the net velocity is what they're going to show there. I don't know what this picture is supposed to be, but your net velocity is going to be something like that black line. It has a component due to your traveling sideways and the outward component that you threw. Now, what about point B? Point B is also traveling sideways. And how's the speed of point B compared to the speed of point A? It's faster because VB is going to be radius B times omega. VA is radius A times omega. So B is moving sideways faster. So as the ball travels out toward B, it stays fixed in its sideways velocity, whereas B is going at a faster rate. So by the time it gets out there to the radius of B, B has moved farther sideways than it has gone. So as somebody on the carousel would observe, it appears that when you threw that ball straight at B, it arced away and went behind it. Now, if B was throwing the ball toward A, what would have happened? It would have veered ahead of it. And so that effect that if you're in the rotating reference frame, it looks like it veered is the Coriolis effect. So it's very real. It's the fact that you yourself were accelerating. If you're going in a circle, you're accelerating toward the center. That made it so it appeared to veer. If you were standing on Earth and watching, you would have said, no, it went straight in the horizontal plane. It was only the vertical plane where it didn't go straight. So it's a reference frame issue. Well, why is that important? Well, things like, we all know that when you have water go down the sink, it goes better if it swirls and makes a nice little eddy. And in the northern hemisphere, those eddies are supposed to go as you look down counterclockwise. And we really observe this in our toilets, right? Actually, we got new toilets in our house and they don't swirl. Never seen that before. But you see that in your toilets, right? And so we all assume, well, while we may not have heard the term Coriolis effect, that that's the reason. As soon as we learn Coriolis effect, your physics teacher usually says, and that's why your toilet swirls the way it does. And so, my 18 years ago, The Simpsons took this one on. They had an episode where Bart learned that the toilets swirl because of this Coriolis effect. In the southern hemisphere, if you think about the northern hemisphere, if you throw the ball north, it's going to be going to a smaller radius for the rotation about the Earth's axis. In the southern hemisphere, if you throw the ball south, it's going to a smaller radius. What does that mean? It means that the deviations in opposite directions in the northern hemisphere compared to the southern hemisphere. So the swirling should be in the opposite direction. And so Bart is really, really curious. And so he makes a collect phone call to some naive kid in Australia who stays on the phone for like an hour with the collect phone call to check the toilet and see what direction it rotates, and causes an international incident because of the incredibly large phone bill. Which, let me tell you, they used to be big. These days, you don't know. I used to have a girlfriend in Japan. I would call her like an hour a month, and it was $300. Yeah.
Why do you buy plane tickets?
Because I was, no, that's good. I was in school. I was planning on going to visit her, but then things happened before that happened. I hate going to visit her. She had been a student at the same school. It's not like it was 10 pounds. Anyway, that's not important here. Not important at all. So, in the episode, in the end, Bart gets flown down to Australia to try to make amends, causes more international incidents with him and Homer, and then they look at the toilet in the U.S. Embassy. They've got it all rigged up so that it flushes the right direction. Well, the truth in all this is your toilet is rigged to rotate the right direction. The Coriolis effect is so weak that it might be, 15.5% of the time it would swirl one way, and 49.5% of the time it swirl the other way because of the Coriolis effect. Very small effect for something small like a toilet. Because how much closer is the water getting to the center of the Earth when you flush the toilet? No, not very much. So they make the toilet so the water comes out with jets, making it go in the circle so it will make the nice swirl. But is it real? You bet it's real. We see its effect when we see things like tornadoes. With tornadoes, you have air that comes in. As the air comes in the northern hemisphere, you're going to have the deviation going like that when it goes in. When it goes out, well, you have the other side. And that air coming in to the tornado causes it to rotate. And so that's why the tornadoes rotate. Tornadoes in the northern hemisphere rotate the opposite direction from tornadoes in the southern hemisphere because the scale of tornadoes is very big compared to the scale of your toilet. So the effect is very strong for the tornado. Now, it also causes cool things. How many people have taken a flight like from here to Asia? Clearly, like Gila, I live there. Chilapa, I live there. Of course I've taken that flight. You notice that it takes a significantly, that the time flying from here to there is significantly different than the time flying from there to here? Why? The jet streams. What's the jet stream? On Earth, we have warm regions. We call those the tropics. Why are the tropics warmer? Because they receive more direct sunlight throughout the year. So because they're warmer, you have air gets hot, that hot air expands, it floats up on the colder air, and so you have a general rising of air over the equator. So if you look at this picture here, you see that rising of air over the equator. But then, of course, what has to happen? That hot air that rose then heads north or south, depending on its hemisphere. Air actually doesn't really cross the equator. It goes up and circles back to the side it came from for the most part. So you have air that at the high altitudes in the northern hemisphere is heading north, in the southern hemisphere is heading south. So you have this, and because of the Coriolis effect, it starts to deviate. And so this air at the high altitude is going to deviate to the east as it heads north. Then it comes down around 30 degrees north or south latitude. Why does it come down? Well, you had hot air that went up. As it went up, it expanded. When it expands, it cools. When it's cool, it can't hold as much moisture, so the water drops out. Hence, in tropical areas, you have a lot of rain because you have hot, moist air that rises, cools, and drops the water out. So then you have cold, dry air that's heading north or south. In the northern hemisphere, it's heading north. And because it's cold, it gets colder still, and it starts falling. Now, as it falls, it gets compressed. When you compress the air, it gets hotter. You probably noticed with the bicycle pump, the pump gets hot when you pump it up. So now you have hot, dry air coming down. Hot, dry air means no rain. So it makes deserts. So that's why it says dry there. You tend to have deserts about 30 degrees north or south latitude because of this air circulation. But then that hot, dry air comes back and feeds the equator, or it can go north up here, and so you have more Coriolis effect. So at the high altitudes, you'll have a wind that in the northern hemisphere, if you're somewhere like we are, it's going to be heading east for the high air winds. And down the surface, it'd be heading west. So that's why the airplanes travel faster one direction or the other, because you're going either with the Coriolis effect jet stream or against it. And yes, it does say jet streams on there. I didn't notice that. But hey, we got it covered. So I wanted to point out the hurricane. This was from 2 days ago because I planned on talking about this in class 2 days ago. We have 7 minutes left in this class period, so I'm doing well. I thought I'd point out, anybody know what that is? Okay, I got to use a different color because that's not very easy to see. St. Croix, which is part of the U.S. Virgin Islands. So you can see that this eye was barreling in on that island. I haven't heard anything about the damage there, but that is U.S. soil. There have been people who've been really upset when people talk about, it made landfall in the United States, when it made landfall on the contiguous 48 states. Now, St. Croix is not a state. It's part of the United States still. And of course, what's this baby right here? Puerto Rico. What do they not have in Puerto Rico right now? They don't have electricity. They also don't have a desert, but I don't think that was at the top of anyone's list. Because they got really hammered by that tornado or hurricane. Why did the hurricane occur? Hurricanes occur because you have to have warm sea temperatures to drive the hurricanes. A lot of people say, these hurricanes are a sign of global warming. The scientists say that global warming, warming trends occur, but the actual hurricanes are not actually indicative of global warming themselves. I actually don't know exactly why they say that. It's not my area of specialty. But you have to have a temperature anomaly that's actually 20 Fahrenheit above the average surface temperature of the ocean. It's only a few degrees, I think, above the water surrounding. But that hot water then heats the air above and drives the upward motion. You also have to have an atmospheric instability up at the top for it to form the cyclone, and high humidity in lower and mid troposphere. The troposphere is the lowest layer of atmosphere. That's where all of our weather occurs. So that said, let's answer a question, and then we'll start talking about new material. So why do we observe the Coriolis effect if the Coriolis effect is fictitious? It's Coriolis force is fictitious. Right, so the force is what's fictitious. I can't write on that. The force is what's fictitious. The effect is real. Okay, missing Brittany, Michaela Cohen, and Augusta never came. And right, because Chilapa never answers. Her brother answers every class period, though, just in case you're wondering. Okay, so 22 people said because the Earth is rotating. Ms. Cohen, give us just a brief rundown. What causes this Coriolis effect?
We just mentioned earlier about the equator and how it's different with the rotation only on the axis of the Earth, the axis of the Earth, the northern hemisphere and southern hemisphere. Other than that,
Okay. Okay, so I mean, she got the things that were important for answering the question, did she not? Yes, she did. The Coriolis effect is caused because the Earth is rotating and it requires something to either move closer to or farther from the Earth's axis of rotation. So if it goes from the equator toward the pole, it's going to deviate ahead or toward the east. If it goes from the pole toward the equator, it's going to deviate behind or to the west. Energy. Energy is very important. Over 99% of the Earth's energy budget comes from one source. What's that one source? The sun. Over 99% of our energy budget comes from the sun. Oftentimes people don't recognize, they say, well, we burn a lot of oil. And where's that oil come from? The oil was originally, depending on the grade type of stuff, probably an animal. That animal ate plants. Those plants got their energy from the sun. And so through a very indirect process, that oil is the result of the sun. Much more direct, solar power. A little less direct than solar power, wind power. Wind power is generated because we have heating from the sun, which causes air to flow, and then we use something to gather that. The small fraction that remains comes from nuclear energy. So we are going to spend, next week with T3, I keep saying doctor, you will study energy carefully. I will just introduce work, and then we'll have to go. Work is a force that results in motion. So if you have a force, that doesn't mean you have work. I'm standing on the floor right here. I'm not moving. No work, because there's no motion associated with the force. But there's something more to it. The force has to be parallel to the motion. So if I have this box sitting on my hands, and I walk at a constant speed, there is motion, right? But what direction is the force I'm putting on the box? Up. And what direction is the motion of the box? Horizontal. Those are perpendicular. No work. Force has to be parallel to the motion for there to be work. So if I'm pushing a car and I'm pushing the direction it's moving, then I do work. What if I'm pushing a car and it's moving me into me? You know, I'm trying to push it up the hill, but it's rolling down into me. Then there's negative work. If the force is opposite direction to the distance, then it's a negative work. So in math, in our linear algebra, we have a way of writing parallel. The product of two vectors, there are two ways of multiplying vectors. You can multiply the parallel parts or the perpendicular parts. A dot means multiply parallel parts. So we call this a dot product. What are the two common signs we use for multiplication? Okay, there is parentheses. That was one I was considering not as common. Obviously got an answer, so it's reasonably common. We use a dot or we use an X. With the X, we call it a cross product, and it's multiplying the perpendicular parts. So work is force times the parallel distance, and Keith will have to take over from there.